So we have defined gradient of a scalar, am I right? So where t is any scalar field, we defined gradient of a scalar. That gradient was a vector, am I right? So that was equal to x cap into dou t by dou x, or dou t by dou x into x cap, whatever, okay? Y cap into dou t by dou y, so plus z cap into dou t by dou z, isn't it? We have defined this one as gradient of a scalar, isn't it? So where t was a scalar field which was a function of x comma y comma z, okay? Now look at here, after seeing this what you call gradient formula, okay, what we do is we define a operator, del operator. We call this one as del operator, okay? That del operator we are going to define like this: x cap, this is an operator, okay, just like derivative operator, d by dx, d by dy, like that, okay? So we have to see this one as an operator that you are going to operate on something. Is that okay? Operator, okay? So del vector, so we are going to write like this: that del operator, that's equal to x cap into dou by dou x plus y cap into dou by dou y plus z cap into dou by dou z. We are going to define an operator after looking into this one. Is that okay? And this is one of the operations that can be done with this operator. This gradient of a scalar is one of the operations that you can do with this del operator. Yeah, we are going to use in quantum mechanics. So three-dimensional your what you call momentum operator minus I h bar del. This is the operator. This is the operator, the same del operator. Is that okay? Now look at here. Now what I am saying is this is one of the operations that can be done with this del operator. You can do many other operations also. So just like if you have a vector, okay, you can multiply that vector by a scalar, am I right? So if you have two vectors, you can take dot product between them, am I right? And if you have two vectors, you can take a what you call cross product between them, am I right? You can do a lot of things with a vector, isn't it? Similarly, you can do a lot of different types of operation using this del operator. This gradient is one of them. Let me take this one as first one, or let me list it here. So gradient of a scalar. So if you have a del operator, you can do a kind of operation on a scalar, okay? You can find a gradient of a scalar which is a vector actually. Is that okay? First one. The second one, again just similar to A dot B, okay? In case of vectors, just similar to A dot B, you can define what you call, again, you will define a kind of dot product of this del vector with a vector field, but it is not this kind of dot product. It's a kind of operation actually that we do on a vector field. Is that okay? So this is a kind of operation that we do on a scalar field. The resultant is a vector. So there is one more kind of operation that you can do with a del operator on a vector field. It's a kind of dot product, okay? Result is a scalar. We call this divergence of a vector. So this is other type of operation that you can do with a del operator. Third one is curl of a vector. Curl of a vector or curl of a vector field, okay? So that means it's a kind of article. If you have two vectors, you can take cross product, am I right? That cross product is again a vector. Like that, if you have a vector field, you can do one type of operation with a vector field. We call it as curl of a vector field, which is again a vector, okay? This is a scalar. So this is a vector we have seen. So this is also vector. We call it as curl of a vector field, okay? You can do these three things with del operator, okay? And all of these are, look at here, a kind of derivative only. They have different interpretations, okay? Geometrical and other interpretations, okay? So, but all of these are point operation only. Point operation means you can take gradient of a scalar at some point in space. You can take divergence of a vector at some point in space. You can take a curl of a vector at some point in space. Are you getting a point? Just like taking derivative at some point. Okay, these are point operations. And this is a vector, this is a scalar, this is a vector. Is that okay? They have their own, what you call, interpretation and applications. Is that okay? So this is similar to taking, again, these two are very similar to taking dot product and cross product, okay? Even though their formula also looks exactly similar. Is that okay? The, what you call, mathematical, so elaboration of this divergence and curl, that also looks very similar to your dot product, okay? So shall I proceed? We have already seen the use of gradient of a vector, am I right? Which helped us to find infinitely many derivatives in case of 3 dimensions, isn't it? Directional derivative and all. So we have already seen what is gradient. Now we shall get into the divergence of a vector. Is that okay? Yeah, any questions? The divergence. The divergence. Okay, we have seen already, isn't it? Again, now we shall see what is the divergence. The divergence, whatever you do, so you are going to, it's a kind of operation that is done on a vector field, am I right? So that's why first we shall define that vector field V, okay, small v, okay, take it as a small v. So that's equal to Vx into x cap plus Vy into y cap plus Vz into z cap, okay. All of these three are function of x, y, z. I hope I told you the definition of vector field, am I right? Vx means Vx as a function of x comma y comma z, okay. So that means vector field is a collection of 3 set of functions. That's how I told, isn't it? Vx is also function of x, y, z. Vy is also function of x, y, z. Vz is also function of x, y, z, okay. Vector field idea, okay. So now look at here. This divergence of a vector field, it's a kind of dot product taken with this del operator and this one. You can write the del operator first, x cap into dou by dou x plus y cap into dou by dou y plus z cap into dou by dou z, okay. So you can take some dot product with what you call Vx into x cap plus Vy into y cap plus Vz into z cap. Is that okay? Now x cap dot x cap equal to 1 dou by dou x of Vx. That's how we write. Dou Vx by dou x plus dou Vy by dou y plus dou Vz by dou z. Each of these Vx, Vy, Vz are a function of all 3 coordinates, okay, x comma y comma z. So this is how we define divergence of a vector field. Isn't it? You better to write a small v because I'm going to take big letter V. It's capital letter for us. Okay. There are 2 definitions that I can give you about this divergence. Okay. Those definitions are on its geometrical meaning actually. Is that okay? The first definition is as we have taken in the last class. Am I right? So what is this one? Del dot V, that's equal to limit capital V, volume tends to 0, 1 by volume into surface integral of, okay, where V is the volume enclosed by this closed surface integral of V dot dA. Am I right? What was this V dot dA? Actually it was a flux through that closed surface. Am I right? Where dA vector should be chosen outward from the region of the surface, closed surface integral. What is this one? Outward flux through the surface, okay, per unit volume, flux per unit volume, flux density, okay. So, or you can write like this actually, when you make that volume very 0, this flux also becomes very, very small, am I right? This will become a kind of derivative actually. What I can write is, you have defined this one as a flux density, am I right? So what I do is, if you take this limit, this will become, so this is actually a flux actually, okay, or I can write like this, limit volume tends to 0, 1 by volume times, okay, flux through the surface, where V is the volume enclosed by the surface. Okay. Now what I do is I can write this one as some d phi. Once volume tends to 0, this flux also becomes very small. Am I right? Small amount of flux divided by small amount of volume. Is that okay? Not that correct, but I can use that one later. Okay. In case of Gauss theorem, I can use that one. So that's why the first definition was, can you write down again? So del dot V, okay, del dot V is volume density of outward flux. Volume density. It's a kind of density of flux, am I right? Volume density of outward flux. Volume density of outward flux of a vector field from an infinitesimal volume element, from an infinitesimal volume around a point in question. Around a point in question. So that's the first what we call meaning of divergence of vector field. Okay, it's a volume density of outward flux from an infinitesimal volume element from a point in question, because this is a point operation, am I right? It's a kind of derivative, it's a point operation. You can define divergence at one point in space, am I right? So you have to, again, if you want to define a divergence at some point in space, if you have a vector field, okay, so what you have to do is you have to consider infinitesimal volume element, okay, around the point of interest, okay. Then you have to find outward flux. This outward flux, I think I defined this one, isn't it? Closed surface, you have to take a closed surface. Is that okay? Outward flux of a vector field from an infinitesimal volume around a point in question. Is that okay? That's the first definition. Is that okay? Wait a second, this divergence will talk about source. That's correct. You don't call it as a source field, this is a scalar field, am I right? You can, I think, have you seen that one anywhere in any book? Source field? Yeah.
Sir?
Yes.
Sir?
Yes.
Sir, it is like some source from where some field is diverging, sir.
Yes, wait a second. So let me just give that idea. Now look at here. So let me take some example. In the example, so this will come, okay? Wait a second. Now look at it. There is another what you call definition. Let me take this. So that is a definition. Very, very simple what you call definition. Okay. So that means again, these two definitions are similar. Okay. So this divergence is actually a measure of. It's a measure of how much a vector field. How much a vector field spreads out or diverges from the point of interest. From the point of interest. It's a measure of how much vector field V spreads out from the point of interest. If it spreads more and more, then divergence will be more. Outward flux of the small volume element will be more, isn't it? So exactly, you can link with the earlier definition. Now, to get a feel of this divergence, we have to take some example. We have to work out something. Is that okay? We have to work out something. So shall I write it here? So del dot v, that's equal to dou vx by dou x plus dou vy by dou y plus dou vz by dou z. Is that okay? Now let me take one example. Suppose my vector field is uniform vector field, v naught into x cap, suppose. Is that okay? So that means, suppose let me take this is x cap direction, okay? My vector field is uniform. How did I, drawn uniform vector field like this? Am I right? Suppose if you want to make more lines, but keep density same. Is that okay? Can I call it as uniform vector field? So spreads out everywhere actually, okay? So it is there everywhere, uniform vector field. Okay? I have to make density of the field point, okay? Now, wherever you take, so just assume that this is infinitesimal volume element. I can't draw much field lines, okay? Just assume this is one infinitesimal volume element, okay? And wherever you take that infinitesimal volume element, number of field lines which are piercing from one surface, that's equal to number of field lines going from other surface. Inward flux is equal to outward flux, you can say that one, or net outward flux is 0. Net outward flux is 0. Or volume density of outward flux is 0. Isn't it? So that's what you can physically see here, isn't it, from its definition. And we shall see the what does our mathematics says, okay? Del dot v is equal to, what is this one? Dou vx by dou x plus dou vy by dou y, and all this equal to 0, am I right? Because you can write it as vx into x cap, where vx equal to constant. Okay, it is not changing. Is that okay? It is not changing. Okay, divergence vanishes here in case of uniform vector field. Okay, that is because of the fact that if you take infinitesimal volume element around any point, okay, number of field line going into that region is equal to number of field line going out of that one. Net flux is 0. Net outward flux is 0, isn't it? We call that one as net flux, am I right? Again, if you have any closed surface, okay, if you are placing that one in a vector field, okay, so then what you did, you have defined dA vector like this, and you have taken dot product with vector field and the dA vector, and then you have integrated closed surface integral. We call that one as total flux, am I right? So total flux throughout the surface. Suppose if you name the surface as closed surface integral, isn't it? Flux through the surface, isn't it? Now you just take an infinitesimal volume element, closed surface, okay, net flux is 0, or volume density of outward flux is 0. Is that okay? So divergence is 0. That's one of the example, okay? Now let me take one more example. Look at here. It's quite difficult to do this one actually, but still let me try. Again, yeah, speak out. So x into x cap. Can I write like this? Now mathematically, what is divergence? Del dot v is equal to dou vx by dou x, that's equal to 1, am I right? That means volume density of outward flux is non-zero here, okay? Net outward flux exists if you take infinitesimal volume element, okay? So that, again, now let me try to draw that one. Let me try to represent this kind of a vector field, okay? Look at here, let me take this one as a origin, okay? This one as a origin. Along x-axis, okay, your vector field strength is increasing, am I right? Can you see this one? When x increases, field strength is increasing. Can you see that one? Yes. Now what I do is, to show that increase in the field strength, let me do some idea. Okay. that okay? So what I am trying to show here is density of field lines are increasing. Can you just see this one? When you move further, density of field lines are increasing. Again, I can't draw very ideal diagram, but I can do some approximated one, isn't it? When you move along x-axis, okay, vector field strength is increasing. That I have shown by density of field line. Okay. Now look at here. So since density of field lines are increased, vectors are parallel to each other, isn't it? You can see here, vectors are parallel to each other. All vectors have the same direction, okay? Now look at here, but density is increasing. Vectors are parallel to each other, density is increasing. That means, so these vector fields are created in space. They are generated in space. There are sources here, sources of the vector field here. Earlier, sources of the vector fields were not there in case of uniform vector field. Okay, so there were no sources actually. Again, as I told, the divergence will talk about source. Am I right? If you have a uniform vector field, okay, again, these vector fields are started from some source which is very far away, and they are ending at infinity. Here there are no source of vector field. So that's why your divergence was 0, because divergence will talk about whether there is a source of vector field or not. In case of uniform vector field, if I write V is equal to V naught into x cap, okay, there was no source in our region of interest. This was generated by some source somewhere at minus infinity. This vector field will end at plus infinity. Is that okay? Speak out. So there was no divergence, means there was no source of vector field here. Because there is no source of vector field, wherever you take the infinitesimal volume element, okay, number of field line piercing one side of the surface is equal to number of field line going through other side of the surface. But here you have sources. So that's why even though vector fields are parallel, look at here. So since there are sources throughout this region, I can't show that sources throughout the region. I can only do some symbolic one, okay. Because there exist sources, look at here. Suppose if you, find, if you take infinitesimal volume element, suppose somewhere here, okay. Can you just imagine this one? Is that okay? Now, number of field lines which are going out from this surface, is that okay? That is more than number of field lines going into that surface. Is that okay? Speak out. So that's why there exists a divergence. We call there exists a divergence. That means there exists a source of vector field. Look at here. This is a constant, am I right? This is a scalar field actually. Divergence is a scalar field, but it's a constant, am I right? That's equal to 1. Whatever the point you take, it's equal to 1. So that means whatever the point you take in space, that is a source of vector field. All points in space are source of vector field. They are generating vector fields actually. So here, no source of vector field at all. Vector fields are generated somewhere. It ended at infinity. It started from infinity and it is ending at infinity. Find the difference. Yeah.
Sir, I mean, can I take one point from the
No.
And in the near that one, it is very strong, and outward it is
Look at here. Here I have drawn the representative one. So actually, I may have some gap between these two. So don't take one infinitesimal volume. There is a gap. Number of field line inward equal to number of field. Don't argue like that. I should have drawn this one entire region, okay, very close to each other. That I can't draw on the board. That's why I have taken that my infinitesimal volume little bigger, so that I can show number of field line into that one is less than number of field line which is going outward. Are you getting a point? It's a symbolic one. Actually, if you see this mathematical expression, divergence equal to 1, independent of x, y, z, that means divergence exists at each and every point in space. Wherever you take this volume element, you get net outward flux. Number of field lines going outward from that volume element is more than number of field lines going into that one. So there exists net outward flux. Here.
Yes, sir. Yes, sir.
Speak out again.
Sir, I'm saying in second case, this infinitesimal volume treats like a source.
Volume element is just to measure divergence, okay? Volume element is not a source. I am saying there are source of vector field. Source of vector field means that creates vector field from space, from a spatial point that creates vector field. Just like a charge which creates electric field. Just like a current element which creates magnetic field. Is that okay? We call them as a source of a vector field. There exists source of a vector field and divergence will give you the information about that source. That divergence equal to 1 means, okay, at each and every point, what you call, you have a source. Is that okay? This is a representative volume element, okay? Are you good enough? This is a representative volume element to measure outward flux density, okay? Volume density of outward flux. Is that okay? So you can write this volume as dV, okay? You can find flux through that one as d phi net outward flux. You can take the ratio. You can call it as a kind of flux density, isn't it? Flux density rho phi, can I say like this? Volume density of outward flux. And that volume density of outward flux, that's equal to non-zero. That means wherever you take infinitesimal volume, you will get outward flux. So observe that fact. That's a very good example. Okay. Actually, here I have taken some gap. Am I right? From here to here, from this point to this point. Okay. So you may see that your fields are uniform. Not like that. Okay. You should draw this one very close to each other. But I can't do that one on the board. Is that okay? So from this plane to this plane, am I right? You may see that vector fields are uniform. Not like that. Okay. Vector fields are not uniform. Okay. They are continuously, the strength is increasing. But I have drawn only representative. Okay. Speak out. Now, this is a one. Yeah. Speak out.
So these field lines are produced from a single point source or multiple point source?
Not even multiple point source. You have source everywhere. Look at the value. This is.
Then sir, we can take one example. If I will take one point charge. And
no, wait. I'll come to point charge. Wait a second. Now, what I am saying is, see the divergence. Divergence equal to 1. Everywhere it is 1. Am I right? Here also 1. Here also 1. Everywhere at each and every point. That means you have a source at each and every point. That's what I am saying. Wait a second. I'll come to charge now. Is that okay? Now look at here. We shall study the divergence. Yeah, speak out.
This method is also used in calculating the density in laboratory, or is it only mathematical?
No. A kind of bookkeeping. Okay, you don't count field line. I told, isn't it? Number of field line that you draw, that depends on how big your paper is, how sharp your pencil is, isn't it?
Sir,
So those are representative things. Only we can talk about proportionality. Okay? Yeah, speak out. Now look at here. Suppose let me take a vector field like this. Vector field is equal to R vector. That's equal to X into X cap plus Y into Y cap plus Z into Z cap. Am I right? Y into Y cap plus Z into Z cap. What is my vector field? That's a, what do you call, so position vector field. Can I say like this? Position vector field. Okay? Or radial vector field. Okay? So now what is the divergence? Can you quickly tell me? Speak out. That's equal to 3. Am I right? Dou Vx by dou x 1, 1, 1. Isn't it? That's equal to 3. So that's, but again, just try to draw this one. It's very difficult to draw this one also. Okay? Look at here. So if you want to draw, you have to draw it like this. Look at here. Okay? Is that okay? I mean, that is one of the representation that I am doing here, okay? Need not be like this, okay? That means there are sources everywhere, okay? So wherever you take, okay, suppose let me take some radial part like this, okay? Again, wait a second, let me draw a little better diagram, okay? Again, as radial distance from the origin increases, okay, vector field strength is increasing, am I right? Speak out. So let me draw it like this. Okay. Are you getting my idea? Field lines are generated either because we have divergence non-zero, okay? Again, generate much more. Is that okay? So to represent that vector field, you should go for this kind of idea actually. Is that okay? Now I hope you can see that one, am I right? The density is increasing. Yeah, it takes a lot of time. But density, can you see that density is increasing? Actually, I should make this, what you call, these circles as close as possible actually, because everywhere you have a divergence which is equal to constant, am I right? Look at here. Isn't it? Is that okay? Field lines are generated in space actually. Looks like corona. Yes. Now look at here. What I'm trying to say here is, when you move away, vector field strength is, look at here, what is the magnitude? Magnitude of R. So that's equal to root of x square plus y square plus z square. Am I right? That's increasing, isn't it? Strength is increasing. Okay. If you take a volume element, okay, anywhere, infinitesimal volume element, number of field line into that one is less. Number of field line which is going out from that one is more. Okay. I haven't shown the direction. Okay. It is outward. Okay. The direction of field lines are outward. That I haven't shown. Is that okay? You have a divergence. Wherever you go, you have a divergence. That's equal to 3. Is that okay? Net flux around the infinitesimal volume element is equal to 3, or outward flux density is equal to 3. Is that okay? Now look at here. This is the, what you call, nature of this vector field. Am I right? I got the divergence 3. Okay. Now let me go for vector field, electric field due to a point charge. Yeah, speak out.
Sir, near the point source, field line will be more.
Near? Wait. I will get into the charge now. Okay, wait a second. So just see this expression, okay, and work out, okay. Just see this expression and try to interpret, okay. This is a radial vector, am I right? Whose length is increasing, am I right? I mean, whose strength is increasing, isn't it? Think like a vector field, okay. Yes. Now what I do is, let me take a, what you call, charge which is placed at the origin, okay.
Sir,
Yes.
one more example, sir. If the vector field is equals to minus x cap and plus y cap, in that case the divergence is equals to 0. Then how can we?
So it will somehow compensate. Is that okay? It will somehow compensate. Net flux will be 0 somehow. You are varying in both direction. Am I right? So somehow it will compensate actually. Okay. Let me try. If there is any, what you call, software to draw this kind of vector field, because this vector calculus is used in computer programming to generate what you call, kind of random pictures and all actually, that you can find as a screen saver many times, isn't it? That kind of picture actually. Okay, wait a second. I have placed the charge at the origin. What is the electric field at this point? Okay. Now look at here. If I place charge at the origin, what is r prime vector? Speak out. If charge is somewhere here, you can draw r prime vector. If source charge is on the origin, then r prime vector is a null vector. Am I right? Okay. So then your italic r vector is equal to r vector, because r prime vector is equal to 0, isn't it? So that's why to find electric field at this point, okay, so you can write electric field due to this one, that's equal to 1 by 4 phi epsilon naught, okay, q by r square into r cap. But since r prime vector is 0, italic r vector is same as this r vector. Is that okay? That's why this is equal to 1 by 4 phi epsilon naught, okay, q by r into r cap, okay. Now I will not care about these constants, okay. Let me just care about that vector part. What is that vector part? I'll keep q by 4 phi epsilon naught outside, r cap, speak out, r square here, okay. Let me concentrate on this part. Now I know that, okay, my physical intuition says that, okay, there is only one source which is at the origin, am I right? There are no sources other than the origin, isn't it? Now look at here. If you take the, what you call, divergence of this one, divergence of r cap by r square, that is nothing but taking divergence of electric field, okay. So that will be 0 except at the origin. Why? Electric field should be generated by this charge and they should end at infinity. That's how we draw, am I right? Due to any positive charge, we draw electric field like this, am I right? Speak out. Is that okay? Electric field will be generated by that point charge. It will end at infinity, isn't it? So now look at here. If you take what you call your infinitesimal volume element, what will happen is number of field lines going into that volume, closed volume region, that's equal to number of field lines going out of that one. Because these field lines are not generated in space. This equal to 0. This is saying that these field lines are not generated in space. There are no sources in space. So a source is there here only. That's why if you take your volume element, infinitesimal volume element, anywhere except at the origin, you will get what you call net outward flux 0 only, isn't it? But if you take your infinitesimal volume element at origin, okay, then look at here, you will have net outward flux. Everywhere your field lines are going outward from that region only. If you take what you call that volume element anywhere else, number of field lines going into that one is equal to number of field lines going out of that one. But if you take that volume element at the origin, okay, infinitesimal volume element at the origin, you will get net outward flux. That means there exists source at the origin. There exists no source nowhere else. Field lines are started from this one. Field lines are ended at infinity. Field lines are not generated at midair. After seeing this one, after seeing this expression, I can say like that. It's an ambiguity. Actually, this you can't use this derivative kind of formula at origin actually. Okay, but you can say this equal to 0 other than the origin. For the any point other than the origin, you can just write this equal to 0. Definitely, you can write it. Is that okay? Work out this one. Work out this one. Is that okay? How this is 0? Using that formula or something. So that's why if you want to draw electric field, okay, first try to what you call explain the behavior of r cap by r square. Look at here. So now we again vector field means, okay, look at here. This vector field, one thing is should show the direction. Am I right? Other one is magnitude. Look at here. When you go away from that one, magnitude of the vector field is decreasing. Am I right? According to this one, magnitude should decrease. It is inversely proportional to radial distance, isn't it? So, how do you catch that, what you call, information? Information that vector field strength is decreasing when you go away from the origin, isn't it? So that is by the density of field line. I think I told that one, am I right? Already. Are you getting a point? Now when you go away from the origin, look at here, field lines, the field densities are decreasing. Here you have more field density. Here you have less field density. Okay? Or number of field line per unit area held what you call normal to the what you call vector field. Okay? So that is decreasing, am I right? You take a unit area, you try to hold that to normal to the vector field, very small unit patch of area. Okay? So when you go nearby, you will have more flux. Okay? When you go away, you will have less flux, isn't it? So density of field line here, which is what you call measure of its magnitude actually. So that density is decreasing when you go away. But field lines are not generated in mid-air. Okay? Field lines are generated from the origin where you have a charge. They are ending at infinity. That's why you have, if you take a divergence at any point in space, you will have 0 because there are no sources there. Yeah, speak up. Now look at here. There are two things here. One is mathematics, other one is physical intuition. Okay? Mathematics says divergence equal to 0. Okay? Wait a second. Okay? And mathematics also says divergence may be non-zero at origin. It itself says that there exists a source at origin. So source should be there at origin. If source is nowhere else, it should be there at origin, isn't it? Otherwise, from where the field lines are generated? Okay? By seeing this one, I have drawn the field lines actually. And I also have the knowledge that source are not there other than the origin from this one. You are not seeing the mathematical expression here. This is 0 except at the origin, am I right? So that's why I have drawn the vector field like that. And now, if I want to account for field strength, how do I define field strength in this representation? I should say that if field density is more, field strength is more. If field density is less, okay, density of field lines is less, then field strength is less. When you move away, look at your density is decreasing. Is that okay? Earlier, this V vector is equal to this R vector. Okay? I have increased the what you call density. Do you remember? When I move away from the origin. Compare these two. There you had a what you call source everywhere. Now you have a source only here. No, wait. It will turns out to be Dirac delta again, which is non-zero only at the origin. I'll come to that point later. But so this derivative, this formula will not work at R equal to 0. Okay? You can't use that formula at R equal to 0. I think you may end up with trouble. Is that okay? The Dirac delta is what we introduced. Okay? It's not well-defined function or it will not come as a well-defined things. Okay? Del dot R cap by R square. Okay? That's equal to 0. So when R vector is not a null vector. Not a null vector means not except at the origin. Okay? Otherwise, you can't do this one at all actually. Okay? So solve all problem, you will get much more idea. Okay? Lot of concepts are there in the problem. Okay? Now from mathematics, I have drawn the vector field. Okay? Speak up. Are you getting my point? I knew that there are no other sources. I also know that vector field strength is decreasing when you move away. Okay? From all of those information, I have drawn the vector field. And now whatever the electric field property you defined in class 12, okay? It will not end at midair. It will start from positive charge. It will end at negative charge, isn't it? If you have a negative charge, you will have what you call field lines which are going in, am I right? If you have minus q charge, isn't it? So in that case also, you have if you have isolated negative charge, okay? So field lines will not end at midair. They will end at this point actually. If you take a divergence at this point, you may get non-zero. Everywhere else, divergence is 0. Okay? That's why divergence will talk about source, whether there is a source or not. Okay? And the divergence value talks about volume density of outward flux.